Hello everyone, good morning and welcome to the latest instalment of the CAT Electric Power webinar series. I'm delighted to introduce today's topic, the power paradigm. Before we get started, I'd like to take you through some of our safety protocols. Please be aware of your emergency exits and your designated emergency caller. For awareness, our meeting is being recorded. Therefore, your presence in today's meeting provides your consent to be recorded. If you do not wish to participate, please can you exit the meeting now. We will be recording today's session for on-demand purposes. Therefore, any external recording devices are prohibited throughout this entire session. We would like to encourage everyone to be safe and to be present during today's webinar. We have a lot of great content to be able to go through with our subject matter experts. And we would encourage everyone to submit questions in the Q&A panel to your right-hand side. And with that, I would like to introduce to you our panel for today's webinar. We have Raphael Timms and Francois-Xavier Saury. Raphael, I hand the floor over to yourself.
Thank you, Onye, and hello, everyone. We are thrilled to be presenting today on this exciting topic as it connects the dots between the diversity of our electric power products and services and today's consumer needs and challenges. So we are excited to demonstrate how efficiently we can address today's challenges due to energy megatrends that we'll present today by integrating our products and services optimized for these specific purposes. But before we start delving into this new power paradigm, let us quickly introduce ourselves. I am Raphael Timms, Regional Sales Manager for our large electric power solutions, and I cover Europe and the CIS territories. I spent the last 20 years in the electric power industry. I have a mechanical engineering background, and I am based in Geneva, Switzerland. François-Xavier.
Yes, good morning, everyone. Thank you for joining. Thank you, Raf. So Francois-Xavier Saury, I'm the Business Development Manager for Caterpillar Electric Power. I'm also based in Geneva, Switzerland, sometimes traveling a lot. And my role is to face customers and help them solve their energy problem, covering Europe, Africa, CIS, and the Middle East.
Thank you, François-Xavier. Let's quickly look at the agenda. We'll start with the definition of the evolving energy landscape, and that will be presented by François-Xavier. He will then continue by delving into the energy megatrends and challenges with a focus on Europe, Africa, and Middle East. Then I will describe the key impacts on the power industry, which includes the distribution generation definition, but also the required flexibility in terms of operation and the role of alternative fuels. And then François-Xavier will conclude with our very adequate energy solutions and hybrid approach before wrapping up on key points. So let's start exploring the new power paradigm. François-Xavier, the floor is yours.
Thank you, Raf. So the energy landscape is changing, and I'm sure the audience is seeing it. And I just summarize a few points. What's happening? So our energy landscape is not only more load, including the data center load, a lot more data to manage, but it's also more load points. So electrical loads are not only increasing, but they're also coming at many different points in the grid, and that is generating challenges. There is also more renewable, and all of these are creating this stability challenge that the grid is facing. That is what we see changing in the energy landscape. So we see what's happening to the grid. So I have here on the right and on the left, in the middle, you've got the grid, and the grid is actually challenged by two major forces. The forces number one on the right is really the electrical loads. Again, not only more electrical loads, the pace of increase of these load is very high, but it's also two things: multiple load points, and also the timing of the electrical demand is changing. In the past, you had low demand at night, and there was an opportunity for low price in certain regions. And now you see we're all charging cars at night, and then the load is becoming more significant. Things like this is happening, and it's changing this, making some pressure and generating challenge to the grid. On the left, on the generation side, you see also challenges, more renewable that are intermittent, retiring of the traditional energy generation, and possibly underinvestment into the hub and spoke distribution and transportation line for power. So the grid is consequently actually pressed between these two forces, and the capacity and its reliability is deeply challenged. The intermittency is something the grid has to cope with, and not only the energy costs is being monitored here, you can witness that, probably all of us can, but it also not only a underinvestment, it's really a lack of investment. The investment that this grid should be making are so gigantic that they're not happening at the right time. So this is really what's happening here, and we see how distributed power generation can help there. It's a key to filling the gap that we see today, and Raphael will be elaborating much longer in this presentation today. Let me move to the next slide. So here are the mega trends. If you want to summarize the presentation of today, it's all about that slide here. On the left here, 3 mega trends, then challenges in the middle, and then what are the impacts for us and how distributed generation can help. So mega trends. Energy demand growth, we'll look at that a bit in detail, decarbonization and flexibility, grid reliability, capacity bottlenecks, demand side flexibility is growing, and last but not least, power industry volatility. These are the challenges that our energy landscape is facing. So what's the impact on that? It's really the help that distributed generation can bring, its flexible operation capability and the fuel flexibility that it can that it allowed, that could be a very great opportunity for our industry here, using distributed generation instead of centralized power generation. Let's deep dive a bit on these items here. We have a bit of time here. If we looked at the first mega trend here, it's the strong electricity growth. Everything is becoming electric. If you look here on the right, EU is expected to grow 16%, EME 29% by the end of the decade. And why is this happening? Multiple reasons. First, the most classic one, it's the economical growth and demographic factors that is growing. So this is naturally increasing electricity demand. That's kind of natural. But what's happening here is other factors are actually adding up to this, and everything is becoming electric. So not only there is a natural growth of electricity demand by population and economic growth, but because everything's becoming electric, they weren't electric before, we continue to do that with electricity, and we need more of that. That means more electricity demand. And last not least, governments are encouraging that. I mean, governments are putting a lot of pressure on carbon footprints in our societies, and that is a good solution to move things to electricity, where carbon footprint is far more manageable. Sometimes you can even completely avoid it, and we'll cover that later. We'll talk to that. So that's the first mega trend, electricity demand growth. The second one was, let me press on that thing. Yes, the second one is really the growth of low carbon. That's the decarbonization technologies. So renewable, just to speak about one, 23% growth in 23% in 2022, 45 expected in 2030. So really a good and major investment in these energy sources to reduce the carbon footprint. However, having these ambitious targets introduces challenges. These renewable sources are yet decarbonize or low carbon, but they also introduce viability, intermittency, they reduce system inertia, and they can create voltage and reactive power problem. For those who have been in Spain in this year, you probably can testimony that this is a challenge, and voltage appears to be the problem here. And the third mega trend, it's really let me see, third mega trend, yes, sorry for that, real quick. It's the demand side. So if you have a flexible power generation, you want to also have a flexible demand, so to adapt this. So the demand side flexibility we see, and these are the European numbers here, you had 10 gigawatts in 2020 of that flexible demand, doubling in 2024, and it's going to be time 5 by 2030. 100 of gigawatt is required to, if we wanted to cope with the flexibility and intermittency of the renewables in our grid. This is something that is now required, is increase this demand side flexibility. So what's happening? What's the challenge of all this decarbonization, flexibility, and energy growth? Well, it's clearly bottlenecks, capacity bottlenecks. The grid is facing capacity bottlenecks. It's also facing reliability challenges. I just mentioned Spain and Portugal in April this year, over 30 hours in some places of blackout, never heard of in Europe for decades and many decades. But it's not new. There was Germany in 2006, Italy in 2011, and for those in South African region, South Africa has been challenged with capacity in their grid since 2008, and that's been more or less solved in 2025 by adding capacity. So the consequence, last not least, all this is driving significant price volatility. So our industry is seeing price going up and down and globally up. If you look at the numbers here, 400% since 2020, and it's been more time where the price, the time with negative price has doubled from 2023 to 2024. Raphael, this is probably the right timing for you to jump in and help us see how distributed generation can help us in these contexts.
Yeah, thank you, Francois-Xavier, and I can certainly do that. Now we all have a crisp understanding of the two main energy megatrends and related challenges. So let's look at their impact on the industry. And a first direct impact is the growth in decentralized power generation. And it's also called distributed generation. And this is what I'm going to define right now. And this energy landscape slide is great to explain what decentralized generation is. But let's start first with centralized generation. So there is actually no illustrated centralized generation on that picture, but we would find these by following the high voltage power lines that you can see on that picture on the right hand side. And somewhere behind those hills, if I click here, then we would most likely find these very large thermal power plants, traditionally powered with nuclear, gas, or even coal. These large and centralized power generation plants would typically deliver power to extended regions or even entire countries. But today, this centralized power generation model, that was the model for many, many decades before, is getting disrupted by its growing portion of renewables, which now includes more and more large-scale solar fields, with illustrated here on the left hand side, and also wind farms that are often offshore and again very large scale. And as per just explained by Francois-Xavier, all these very large renewables, unfortunately, they come with grid intermittency, instability, and imbalances between supply and demand. And all this means risk for the users, risk for the consumers, with three main risk categories that I could list. First one would be more risk of blackouts, as Francois-Xavier just reminded us. The example of the Iberian Peninsula earlier this year is a great and scary one. Another one would be the risk for electric equipment and process efficiency due to disrupted power. So that would impact all industrial application and any critical one. And then last but not least, financial risk. So risk due to energy price volatility because of that supply and demand mismatch. So it often makes sense for consumers to mitigate these increased risks with either a backup power solution, and that would be the case for data centers or hospitals that we can see as illustrated on the screen as well. These are typically equipped with standby gensets, or to produce their own power on site, whether it is prime power only or with heat recovery or combined heat and power, CHP as we call that, to maximize the efficiency and the total cost of ownership, such as, again, examples on the screen here, industrial application, any of these, or greenhouses, for example. But the key here to understand is that many of these power assets close to the consumers to protect their operations would also get connected with the grid and therefore support and protect it. And on top of that, also utilities would also deploy such power assets, genset or energy storage system, to directly support the grid on critical and sensible nodes. And again, that's the example on the right-hand side of the screen, where we see that we have power assets that are directly supporting the grid on a critical power nodes at the specific points close to the lines. And this is really the decentralized or distributed generation model. Now, to make it even clearer, here is a well-illustrated and simplified schematic to really sharpen the definition. So, in brief, the distribution generation model is decentralized small and medium scale generator sets or battery energy storage systems, or even a hybridization of these with even small scale renewables behind where applicable. And that's the box in yellow below the distribution generation banner. And these decentralized small and medium scale power assets are located close to the consumers to support and protect their equipment and operations. Illustrated here with the industrial and residential electricity loads on the last line. And as these loads are connected to the grid, these power assets will also indirectly support and protect that grid. But these power assets would also be directly connected to the grid. And this is well illustrated here on this graphic with the arrows on the side here on the schematic between the grid and the yellow distribution generation box. So all this is, you understood, to address grid intermittency, instability, and imbalances due to the growing portion of large-scale renewables on the grid, as explained by myself and Francois-Xavier. And this distribution generation model comes with the following list of key advantages highlighted in the orange box on the right-hand side. So 3 key points to retain here. It supports and protects both the consumers and the grid. I think that now it's clear thanks to this graphic on the right-hand side. But one important point we didn't talk about yet is the speed of deployment. A genset or a battery energy storage is deployed in about 6 to 12 months, 6 months to a year, versus multiple years of large of development and installation and project studies that will last for multiple years for any national power plant. And last point, but not the least here, efficiency. If we consider a combined heat and power system, this means up to above 90% of total efficiency. That would be considered with an absolute max of 60% total efficiency with a large centralized combined cycle gas turbine. But to effectively support and protect consumers and grid, these decentralized power generation equipment require flexible operation capability. And this is a very important term to understand. It is summarized in the gray box here that these power assets will indeed have to cover many different modes of operations, from standby, which means not running for weeks or even months, to suddenly continuous operations, or even peak shave, sudden, frequent, and high power demand after maybe having remained on standby for several weeks or months. And in addition to be capable of these multiple modes of operations as listed on the previous slides, the most demanding operating mode today when it comes to stabilizing the grid is managing these high frequency of starts and stops with shorter runtime in between. And the graphic on the top right shows today's operating requirements with these 3,000 starts and stops and below 15 hours per year in this what we call ultra flex orange category on that chart versus the continuous rating that is defined by ISO years ago, which would be the blue zone here. So what it is to be retained here is that reciprocating engine-driven generator sets is the best suited technology available today when it comes to flexible operations and related performances, whether it is in terms of number of start and stop, but also transient performances, fast ramp, fast start, efficiency, electrical efficiency, thermal efficiency, or both, and of course, operational cost. That is the most important aspect or specification for a lot of prime application. So that means we will see mainly reciprocating engine generator sets and hybridizations of these deployed in decentralized or distributed generation applications. And that is really the second impact from energy megatrends and challenges, which drives the need for flexible operations capability in order to stabilize the grid. So with that theory, for your information, on the bottom of the screen here, you will find a non-exhaustive list of the best suited gas fuel models from Caterpillar's portfolio, along with relevant performances that are in line with flexible operations. But you will understand that each platform and variant would have their own specific optimum performances. Again, whether it is about transients, starting capability, ramping capability, efficiency, electrical, thermal, operation costs, you name it. You need to basically select the right specification function to the project specific needs. And of course, this is where we can help as the manufacturer, supported by our CAD dealers. Okay, let's jump now to the third, but not the least, of course, impact resulting from the decarbonization megatrend, which is fuel flexibility. And this chart is interesting because it shows the conversation we are entertaining with a large and growing portion of our customers looking into carbon impact of their operations, of course, more and more. So amongst the vast variety, so first, how to read that chart? You can see on the y-axis, it is about measuring the greenhouse gases intensity from very low to very high. So what I was going to say, amongst the vast variety of customers' application we serve, there are three main operational modes. And you will recognize here the two standard ratings defined by ISO that you may know, which are standby, to make it very simple, equipment that ideally never runs. Genset would really be there as backup only to cover any grid or intermediate electrical system issue. And then on the right-hand side, prime power, we like to call that stuff that runs, there to really provide power for substantial time, can be up to 8,000 hours a year, where of course OPEX and total cost of ownership performance are critical. And in between, what we call here peaking, where flexible operation that we just covered is required to, for example, stabilize a grid or protect load from unstable power sources. So as it is well illustrated in this chart, any application with diesel or natural gas is by definition very carbon intensive, whatever the operational mode, standby, peak, or peak shaving or prime, or also whatever the energy conversion technology. You will find reciprocating engine, but also turbine in this example. The lesson learned from this chart is really that with the carbon emissions reduction imperative in mind, it's really with alternative fuels that major differences can be achieved, which is exactly where we have been and still are actively investing today. And these investments brought us to a state-of-the-art level of fuel flexibility and readiness today, as you will see in the next slides, covering the alternative fuels that are listed in the cells on the right-hand side of that picture. So important to know that this very same conversation is also broadening with the data center industry, and I would say even with the data center industry. There is indeed an expanding list of disruption in the data center space, with driving trends also being carbon emissions reduction and demand growth. And these disruptions are shifting the conversation from the traditional diesel standby solution, which is still a vast majority of the data center sites today in Europe, Africa, and Middle East. So we are shifting these conversations to other fuels and operating modes. And beyond these broad conversations we now have with these customers, we are also pushing for substantial carbon emissions reduction across the three main operating modes, such as mission critical and standby data center sites fueled with HVO. HVO means hydrogenated vegetable oil. So basically instead of diesel. And we have that in many large data center projects and sites, many references around the globe today. We are also pushing for green hydrogen or any green gases for, I'd say, new modern solutions like bridge to grid solutions. Bridge to grid are the solution today when the connection to the power grid will be granted to the new data center site only months or years after its commissioning, and the customer traditionally just needing backup genset would also need a solution in the interim for prime power. And of course, based on our expertise, what we are actively pushing and working on is maximizing the efficiency of all these installation and data center installation, and on-site prime power with combined heat and power, and even tri-generation to also generate cold with absorption chillers in order to keep servers at optimum temperature, which is the main challenge of any data center around the world. Now, talking about alternative gases from biomass will also have a great role to play in line with the decarbonization megatrend. It is important to understand that if we let a landfill or a sewage plant vent itself, the emitted methane will have an up to 25 times higher global warming impact than CO2 emitted by using it to generate power. So it is to be emphasized that by just collecting and using biogas, landfill and sewage gases, the environment would be protected on a high level. And also biogas has a very neutral CO2 balance, since only the same amount of CO2 that was absorbed by the substrate when it was growing, plant or organism, only that very same amount of CO2 is emitted during the combustion. So really neutral cycle. And it is also to be highlighted when we talk about biomass that the biomass collecting and processing infrastructure, although it's very well developed in Europe, we see significant untapped biogas potential in Africa and in the Middle East. And we have decades of experience in all gases from biomass at Caterpillar. So our readiness is not a question, but it's important to highlight that we continue to invest in our flexibility and in the robustness with operations of such gases from biomass. Okay, last chapter here in that fuel flexibility topic. The last alternative gas that we want to cover here is really not the least, it's hydrogen. So what's the thing about hydrogen? It is a fuel and can even be used as a base material to produce other fuels. But as written here above the graph, hydrogen is not just a fuel, it's also a great energy storage medium. And as the graphic below indicates, hydrogen beats all other classic energy storage technologies, both in terms of storage time and energy capacity. And what is even more convenient is that hydrogen can be produced locally by hydrolysis with electricity from ideally clean energy before storage and use when needed. Now, with that, why is this energy storage characteristic relevant in the context of today's energy challenge landscape? And this is what we'll be explaining here on the complicated graph on the bottom side that I will explain for you to better understand. So this is again on the bottom left. This is an example of monitored renewable power versus demand on the regional grid over a full year. So the positive values in blue above the x-axis shows surplus of power, so when supply exceeds demand, and negatives in orange means deficit, when demand exceeds supply. In an ideal world, we wouldn't have blue nor orange spikes, but just a flat line, which would reflect an equal supply and demand. But we all know that renewables, unfortunately, don't work like that. So on this graph, we can observe on the left-hand side short durations of mismatches alternating. But we also see other periods on the right-hand side, highlighted in the circle, with longer mismatch durations that could last close to a month on that example. And here is where the aha moment is. With such pattern, what about using the long duration surplus mismatches to generate hydrogen, to then be used to generate power when on a deficit situation? So with this in mind, you understand now the 4-point logical chain on the right-hand side of the slide, with European policies meant to reduce carbon emissions that customers and investors follow as well, of course. There is more and more intermittent renewables on the grid, with more and more demand versus supply mismatches. So more need to store surplus to cover deficits. And therefore, as written on point number 4, hydrogen is an ideal energy storage solution to provide grid stability by effectively addressing the supply and demand mismatches due to renewable intermittency, and this in a decentralized manner with flexibility on fuel and on mode of operation. So we are blending here this way the three major impacts of today's energy megatrends and related challenges. All this, in other words, gensets located close to consumers with critical energy needs, interacting with the grid with flex operations capability, and running on hydrogen produced when the grid is in excess or surplus of renewable energy is an ideal answer to today's energy challenges. So the two questions remaining now are, one, is such hydrogen model ready today? And the very straight and simplistic answer is today would be no. Hydrogen is not readily available yet in large and continuous quantities. Hydrogen is still on its journey to achieve critical mass due to many factors and challenges, such as the infrastructure development costs, which includes production, distribution, storage, but also regulations, safety, governmental policy, and incentives, etc. But the positive message to retain is maybe sooner than later, sorry, with several early stage projects that we start to read in the specialized press. So let's keep ready, and we're getting ready. And the second other question is, where are we, CAT, at with hydrogen product readiness? So to address this question, sorry, just changing slides. To address this relevant question, here is our roadmap to using hydrogen. In terms of technologies first, on the left-hand side, we have fuel cell. We have invested in hydrogen fuel cells with breakthrough projects, even with the data center global account. Turbines, we have now over 4 decades of experience running turbines with hydrogen. And for the topic of the day, reciprocating engine driven generators, or recip genset, as we say. As you can see on the table on the right-hand side, all our gaseous fuel engine platforms are available for up to 25% hydrogen operation today, but also with proven experience with much larger proportion on hydrogen, as you can read in the right-hand side last column. And we have a gas 3516 demonstrator running at 100% hydrogen, while we are looking today for another demonstration site or other demonstration sites with enough hydrogen capacity, because this beast runs at 1.25 megawatt electrical power. So we are progressing towards 100% hydrogen readiness, while the hydrogen infrastructure in Europe, Africa, Middle East develops itself. And the message to be retained here is that we will be ready with 100% hydrogen when the required infrastructure and production will be ready, thanks to all technology validation being completed right now. So all I presented, to conclude my part, all I presented was focusing on demonstrating the adequacy of our gas reciprocating genset to the distribution generation model, and explain how this addresses the challenges of today's energy megatrends, which are, again, electricity demand growth and decarbonization as presented. But beyond gensets and beyond products, consumers, customers, they need complete energy solutions, on which Francois-Xavier will now expand.
Yes, thanks, Raphael. Great insight into the distributed power generation industry here. And again, yes, this is what the customer want. They want a single solution provider from an end-to-end value, someone that is able to master all this is around the wheel. You can see here on the slide, having genset and turbines are able to run successfully on any kind, shape or form fuels, able to integrate renewable energy with our energy storage technologies. Of course, system integration, that means a lot of a control system that interacts with these assets, but also with grids if there is one. And when you have that, you also have an opportunity to monetize these assets. And last not least, the remote monitoring and remote management of these assets, which is really all these items around the wheel. So how do we deliver this? First, a single OEM like Caterpillar is able to master all these technologies at once. And we have the expertise and the experts to develop, integrate, install, and manage all this for the customers. We're also tailoring these solution to customer need, make it easy to do business with. I mean, every customer has a special case. Electricity is so flexible, everyone uses it a bit differently, and that's fine. And we are willing to be easy to do business with, and that how we tailored our solution to customer needs is how we accomplish that. And last not least, our success is actually our customers' success. We are focusing on the customer's energy outcome, and that is what makes them successful. And if they're successful, then we are successful as well. So that's exactly where Caterpillar is putting this together. So let's push the distributed generation model as described by Raphael here a bit further. And what if you had in a single site at a customer site, not at a microgrid level, but at a microgrid level? What if you had all these assets performing at the site level together? So that means you had renewable energy like solar in your premises. You would have an energy storage technology there, a genset technology that would be using what fuel makes sense for that customer, and the controls and the remote monitoring that will make all these works together seamlessly, keeping the system stable and minimizing its cost at every point in time. What if we had that? And that is the microgrid efforts and the hybrid energy solution that Caterpillar has been deploying over the years. And let me show you two examples here. The first one is a grid connected example in the Netherlands near Amsterdam Airport. So near Amsterdam Airport, of course, everyone wants to be located near the Amsterdam Airport or major airports in general, because this is a very successful area to put your business. But the planning and the permitting of the energy supply, electricity supply in that area has been challenged over the years. And it's really today, it's completely congested. So if you wanted to install your business in that area, you can, provided you got the land, but you can't get any power there. The grid is constrained. However, the grid is very happy. If you produced electricity and you had excess, it will be very happy to take and trade that electricity from you. So that's exactly what's happening here. It's an off-taker that is a logistics center, as you can see here on the picture, and the client is actually the owner of the asset, is typically a Dutch PPA company. So what have we delivered here? Of course, on the rooftop, you need to produce electricity with 9 megawatts of solar. We have included 2 gas generators, 2 diesel backups that are actually run only in case of a challenge. They are just backups. 2 Caterpillar PGS 1260, that's 1.26 megawatt of energy storage technology from CAT. And hybrid controllers able to manage all this to make it seamlessly. During the day, the system runs basically on the solar and exports the excess of solar to the grid once the battery is charged. And at night, no solar, of course. And then the gas genset will be operating that side. And if you had excess of electricity, you could actually trade it to the grid, or you can participate in ancillary services to have both the gas gensets and all the energy storage deliver asset monetization in the grid ancillary services in the country. So that's one extremely interesting customer, and we have 4 different sites in the Netherlands around the airport here. Let me move to the next example here. This one is off the grid. It's in the UAE. It's a farm in the middle of the desert. There is water underground, but there is no power. It's too remote. So they are willing to produce mushrooms and lettuce in the UAE to have a local production, to refrain using the import fuel that comes into boats and aircrafts to the UAE. So to do that successfully, you need to make sure that your cost is well below the imported competitors. So food that is imported is at a certain cost. You want to produce these crop and mushrooms and lettuce in that case in the UAE at a lower price point. So there, the way to do that is actually to grow this into a chilled greenhouse, so not warming like we would do in other places in the world, in Europe, for instance. But in the UAE, you need to cool the greenhouse to keep the plants growing. And the energy to do that is typically, when you're off the grid, is typically a diesel generators or combination of diesel generators. And that would be very fine. However, keeping the cost below the importation competitors, you want to look at the sensitivity of that cost vis-a-vis energy cost, because you need energy to cool. If you don't cool, you don't grow. So and then studying the sensitivity of the fuel vis-a-vis the cost, they realize that the connection is too high. So they wanted to disconnect the cost of the crop to the price of the energy. Doing that, they introduced solar in the system. This is something we've proposed, introducing 2.7 megawatt of ground-mounted solar here, an energy storage from the CAT technology, a master microgrid controller, and of course the classic diesel generators. And this customer is successfully disconnecting and reducing its costs by reducing the quantity of fuel burned, about 1.4 million liters of diesel every year. So that's a great example showing how hybrid energy can help you being successful in your carbon footprint. But not only, this is actually an economical case where it actually makes sense economically to put a hybrid system together. Highlights to remember. We're getting at the end of this presentation here, and it's great. So let's see what I want everyone to remember here on the call. First, the energy landscape is focused on reducing carbon footprint. Everyone is trying to get the carbon footprint lower. Everyone is trying to get energy resiliently. You need to be more flexible. You need to introduce microgrid, gas, fuel, recip engines to cope with the instability. And last not least, we've seen that distributed generation can be a solution for that. It can also be quickly deploy and redeploy, and it's very efficient and helps you lower the energy cost. Thank you everyone for attending this presentation. Thank you, Raf. I will pass back the ball to Anya. Thank you.